So I hope my voice is audible, right? Hello. Yes, hello. Can you hear me? Okay. And I hope you can also see my screen, right? The slides are clear, right? Okay. So now we can start the session. So welcome to the week 9 of the NPTEL course, Electrical Measurement and Electronic Instruments. And we are at the week 9 of this course. And this is the live interactive session, and I will be your TA for this session. And so, as you know, these sessions are meant to be interactive. So while we discuss the problems and the concepts, you also should be giving me some feedback, and then we can have a good discussion on those things. So I hope you will do the problems with me, and if you face doubts, just stop me and ask if there are some doubts, right? And if you have some doubts also from the previous week or some concepts you want me to discuss again, then you can just let me know. So before proceeding to this week's problems, I want to know if you have some doubts or you want some concepts again to discuss. You can just let me know. Yes. So any doubts? If you have some doubt, you can just let me know, right? Okay. Yes. Any doubts from the previous week or concepts? Some new persons have joined. So if there are some doubts, you can just let me know. I hope you can hear my voice, because I cannot hear any of your voices. So if there are some doubts, you can just let me know. We can discuss. Any doubts you faced while solving a certain kind of problems, or maybe some concepts you are not understanding, you can just let me know. Because these sessions are interactive sessions, so you should be interacting. Okay, it should not be one way. Yes. Okay, I can see in the comments you are writing, no doubt. Okay. And I'm assuming that till now, whatever we have discussed and whatever problems we have solved, and also the concepts, you are all getting it clear. So let's move to the. Okay. So for some of you are writing that how to study and revise. So we actually have these 12 interactive sessions, each of 2 hours, right? For this 12-week course, plus one session additional. This is an additional session which will be conducted just before the exam in the 13th week, I can tell you. So now we are in the 9th week. So this particular session, which is the additional session, is dedicated for a overall discussion and overall strategy that how can you revise, where we will be merging all the 12-week concepts and just giving you a brief over how to revise and attempt the exam. So it will be a cover up of all the 12 interactive sessions and a revision also for, and obviously a doubt session to get your doubts clarified. So this 13th week is meant for an overall revision, because up to now we are in the weekly sessions, right? We are in the 9th week, so then 3 more weeks will be there. So we'll cover all the concepts of every week and solve the problems. And in the final week, we will be discussing an overall, like a revision, such that all the type of concepts we can merge and then we can have a discussion on those things. So I hope you will also attend the 13th session, which will be the final session of this course, of the live interactive session. So this 13th week will be dedicated for that activity. So any doubts? Any more questions or doubts? So you are not facing problems in solving the assignment problems also, right? After attending the lectures or seeing the live interactive session. Because if you solve with me, I think that you will not get any doubts. But if you don't solve with me the problems, then it will you will do the same error in the exam also. That's why it is important that while I solve the problems, you should be interactive and you should be solving with me. That is the most important thing. Then only you will understand how to solve the assignment problems as well as in the exams. So if none of you have any doubts, we can proceed into this week's problems. So we are in the week 9, and we will be discussing problems on this. I think we can see the slides. Yes, on the digital voltage measurement instruments. So and the problems on ADC and DAC, which is the topic of this week 9. So the first problem I think is visible on your screen. We have a dual slope type voltage measuring instrument, and which is driven by a 5 kilohertz clock given to you, and the voltmeter has an integration time of 2000 clock cycles. That is the total duration you have been provided, and a voltage measurement, that is the de-integration time, because it is a dual slope type instrument. So they have also given you the de-integration time, where you have the falling slope, and that is found to be 190 clock cycles. So actually time is measured in terms of clock cycles, right? Right, in a digital instrument, there is no concept of continuous time. Everything is discretized. So time is also in form of clock cycles. So now you have the reference voltage, which you know is the 4 volt. And given all these informations, you are being asked to find this. Part 1, you have to estimate the value of the input voltage which you are measuring, the unknown voltage signal, the strength of the unknown voltage signal you have to measure, and then the resolution of this voltmeter you have to measure, because these are digital measuring instrument and you have been provided all these informations. So with this information, you have to actually provide the resolution of this voltmeter. Then the third question which is asked is that if the 5 kilohertz clock now, due to aging maybe, slows down by 8%, then the error in measurement in the meter reading of the unknown voltage they are asking. So this is the problem. So how will you solve this problem? I hope you have gone through the lectures and already know what is a dual slope type voltmeter. So it is nothing but you have two signals, and you have one reference signal and one unknown signal. Let us name it Vx. Then you have a circuit arrangement where you integrate this signal. Obviously, it has some integration constant. And then you have a comparator arrangement. And then you feed it to a counter circuit. These two informations. And this will give you the two information. That two information you need. Why? Because you need to measure the duration also, time duration. So time duration, how will you get? Time duration you will get from counter value and clock frequency. These two will provide you the time duration. And the second thing you need is a reference voltage. So reference voltage you have already been provided. This is the reference voltage. So why you need to integrate it? Can you tell me? Yes. You have gone through the lectures, right? So why you need to integrate? I hope you can hear me. Yes. So this is an arrangement to actually compare the unknown signal, we have an unknown signal with a standardized time and amplitude. So this integration is done to compare the unknown signal, which is this one, to a standardized time and amplitude scale. Okay. So the time scale is in your hands. You can integrate it for a certain standardized time scale, pre-specified or predefined time scale, which is predefined actually. So it is a predefined arrangement to compare the unknown signal with a standardized time and amplitude scale. Amplitude scale is standardized as well as time scale is also standardized. So unless and until amplitude and time scales are standardized, you will not be able to perfectly measure the unknown signal value. So the counter circuit is very important, which knows already how much time you have to integrate and then compare to trigger the counter circuit. And as soon as that value is, that time scale is already reached up to that time, then the counter is again reset. So that will give you the time duration in form of time clock pulses. So then using the clock pulses and the known frequency of the counter, you can have the time duration, and the reference voltage is also known. That is how you can measure the value of the unknown voltage signal. So it is a ramp form of measurement where you have a known slope from this integration, and it is an arrangement, a mathematical arrangement you can tell to find the unknown value. So now using this information, can you just tell me how to estimate the value of input voltage if they have provided you separately the integration time, which is 2000 clock cycles. So like this, you have some integration time where you are integrating the signal, and then you have a de-integration time. De-integration time means it is reaching to the zero value. So this is y and this is x. So this time is given as well as this time is also given. And the frequency of the clock is 5 kilohertz, right? So how to estimate Vx? Because Vref we already know to be 4 volts. And obviously it is negative because the slope is falling. So this amplitude is given. So now can you tell me, this T1, T2 are also known. But please be careful, this T2 is what? Can you tell me? Is it from the starting or only this duration is given? By reading the problem, can anyone tell me? Yes, none of you are interacting. Can you tell me whether these times in the form of clock cycles are given from 0 to the integration time and then 0 to the de-integration time, or only the de-integration time and the integration time? By just seeing the problem, can you comment? Yes, hello. Is my slide visible to all? Because I cannot hear your voice. I think you can see my slides, right? Yes, hello. Yes, can you please solve, or can you please discuss how to solve this problem? What are given to you, I hope you understand, because up to a certain time you are integrating the signal, the unknown signal, and with the then you are shifting the switch from position 1 to position 2, and you are de-integrating the signal from the initial value, obviously from this initial value, and then you are going to the 0 point, and both times are specified. So how to find the unknown signal? This time you are dedicating for the unknown signal, and this is given in form of 2000 cycles, and this is given to be 190 cycles, clock cycles, that means. So can you tell me what is the value of Vx? Yes. Yes, solved. Can any one of you just unmute and let me know, because I am unable to understand. Tell me the answer, how to get it. It is simple problem. Okay, some one of you have written some answers. So how you derive the answer? I need the value of Vx. So what information you can get from this? I will not tell, you have to solve and tell me. The answer who have told 1.6 volts is not correct. So what is the time duration? If 2000 clock cycle, then what can I write about time? Time equal to clock cycle divide frequency. That I think you know. Why? Because 1 by frequency is 1 clock time. Now if you multiply 1 clock time with the number of clock cycles, you will get the total time. So that's why total time is clock cycle by frequency. So you need to convert these 2000 clock cycles to a time. Then that means you have to multiply with 1 clock time, and 1 clock time is 1 by frequency of 1 clock. So that means 2000 divided by 5 kilohertz. That is the time taken for integration. And the time taken for de-integration is 190 by 5 kilohertz. That is the de-integration time. You can tile it T1 and T2. Now how to correlate and find the value of Vx? So I can write it C Vx into T, some constant into Vx into T1. Right? Because C is the integration constant, just the same nomenclature I am using as that in the lecture. So if C is the integration constant and you are giving a constant input voltage Vx, then after the integration you have C Vx into T1. The final value I am telling. So y equal to C Vx into T. So at T equal to T1, what I get? Y of T1 is C Vx into T1. So this value, this peak value you already know. Then also you know one thing, that this peak value already known. This is 0. So what I can write? CVX T1, okay, y1 minus y2 divided by x1 minus x2, which is nothing but T2. I am just doing the slope. Don't take the negative part, okay? So this is the height and this is the, consider a triangle, okay? So if I just go with the geometry, then this is T2 is nothing but the slope. And what is the slope? During the de-integration time, it is C Vref. CVx into T1 is the y, T2 is the x. Then what is the slope? This. And also we know that the slope is C times Vref for an integrator with C as the integration constant. And Vref is the input. So now if you equate, then C gets cancelled. And then you have what? Vx into T1 equal to Vref into T2. Then can you help me find Vx value? Vref into T2 by T1. Why T2 by T1? Because T2 and T1 are separately given to you. T2 is this time only and T1 is this integration time only. Discrete times are already provided to you. So now can you give me the value of Vx? Vx is nothing but Vref, which is 4 volts times T2 and T1. But one thing, T1 and T2 are directly proportional to clock cycles. So I don't divide by frequency unnecessarily because frequency will get cancelled in the denominator. So I get T2 as 190 and T1 as T2 is not 190, but T2 is proportional to 190 cycles. So I am taking 190 and divided by T1, which is 2000. And now can you give me the answer in millivolts, because it is asked to find in millivolts. Yes, you calculate and give me the answer. All of you should calculate, unless I will not proceed. So Vx is what in millivolts you give me? Okay, correct, 380 millivolts. So the first part of the problem you have solved. Now try the next part. You try the measurement resolution of this voltmeter. This is the arrangement of voltmeter measuring arrangement, digital arrangement, using a dual slope type version. And now you are being asked to calculate the resolution of this voltmeter, also in millivolts. Measurement resolution index is some voltage scale by some time scale. Obviously, sorry, the rate is some voltage scale by time scale. The resolution obviously is in millivolts only. So give the answer in millivolts. That is the voltage measurement resolution. Resolution of this meter is being asked in the part 2. So you give the answer in millivolts, that what is the least count of this instrument. The least count is being asked. Measurement resolution or least count, both are analogous. So you can give me the least count of this arrangement in millivolts. So try this, how to do. Any idea? None of you are actually interacting, so how can I understand? So part 1 is done, but part 2 you tell me how to solve. Yes? Do you have the idea how to solve? So reference voltage is given to you, okay? Voltage is already given to you. You are trying to measure actually. One reference you already have. So how to calculate the least count? Any idea? So do you understand what is the physical interpretation of a least count? That how much small voltage can you measure? The smallest measurable voltage in this instrument is known as the least count. So what is the smallest measurable voltage in this list, in this type of arrangement? That during one clock period, how much small voltage you can measure? Someone is telling 0.8 millivolt. No, 0.8 millivolt is not correct. Just understand the physical interpretation of the word resolution. What is resolution? Resolution is the smallest measurable voltage of this by this instrument. So how much small voltage you can measure in one clock cycle? Because every clock cycle the value of the meter is updated. Now what is that smallest measurable voltage in one clock cycle? That is the whole point of measurement. So yes. Try. Every one of you should try. Otherwise, telling you the solution will not help. Just try to discuss. None of you are unmuting and discussing, so I am not able to understand. You should unmute and tell something so that I can be able to help you or guide you to the correct thinking procedure. Because that is more important. Otherwise, just marking up the formulas will not help, because none of the formulas will be helpful in the exam. Because you will never get the correct answer by just using the formula. You need to understand the physical inferences of every problem and read the problem very carefully. Because these are the basics. If you understand these kind of problems, then going ahead is a very simple thing. Yes. I want to hear some more answers. And also the philosophy, that how you calculate it. Some of you can also unmute and discuss. I hope my voice is audible, right? Yes, so how to measure the resolution? Some answers? Try. Try solving the part 2. Okay. But please be ready at least with your phone. I think phone has inbuilt mic. So in your phone also you can just see and you use a copy and a pen. All it takes is a phone or a some device and a copy and a pen to interact. Don't need a microphone also. So if you are able to have the correct devices before the session, then I think it will be helpful for you. Through interaction, you will be able to gain more rather than just typing in the chat box or all those things. One-to-one interaction is better. Because see, I am speaking. Otherwise, I can also just write down and go by writing the solution. That will not help, right? You should develop the thinking procedure and try all the problems. That's why I'm asking what do you interpret by the word resolution, and from all the given information, just I told you how to measure the unknown, that is the resolution of this meter. Because what is resolution? It is the smallest possible measurable voltage by this instrument. And how you will get it? By analyzing the smallest possible voltage measuring progress in every clock pulses. Every clock pulse, how much smallest measurable voltage it can actually show or measure. That is the resolution of this instrument. So how to find the smallest measurable voltage in one clock pulse? That is the answer. Okay, we just try and try to determine what is the smallest measurable voltage in one clock cycle. That is only the resolution of this instrument, because if through the complete clock cycle, it will give you the total voltage reading, whatever voltage you are just seeing. But we don't want the total voltage reading. Every clock cycle, what is the smallest amount it is progressing, or smallest possible measurable voltage, that is the resolution. So I give you some time, think and answer, okay, accordingly. So the reference voltage, so how to measure the resolution? We already know the reference voltage, right? Reference voltage is 4 volts. So we know that the clock cycles, we have already seen that we have 2000 clock cycles, right? For measuring unknown voltage. So the minimum measured voltage per clock cycle is nothing but resolution. And it should be the least possible voltage, right? So if I calculate, so what can you get? It is nothing but so in one cycle I can measure how much? So 2 millivolts, right? Yes. So that is how you determine the part 2, that is the resolution of this instrument. And then try part 3, that if the clock frequency is reduced or degraded by 8%, then what will be the error in the meter reading? So if clock new is nothing but 8%, that is 0.92 times if clock old, right? That is 8% slower. So they ask that what is new reading? Can you tell me what is new reading? Just see this equation. We did what? Vx times T1 equal to Vref times T2. So now this T1 and T2 we have been given 2000 and all those things, 190. And these are clocks. We have two kind of readings. One during the integration time and one during the de-integration time. And whatever T1 will come and T2 will come for a particular clock frequency. What is that? I told you T1 equal to clocks by frequency. T2 equal to also clocks during integration time, and this is de-integration time by frequency. So whatever be the frequency, accordingly time will also change. So if frequency is slower, you get less clocks, less time. Similarly, by the same factor, the next time will also be affected. Reduce clocks, reduce frequency. reduced time. So time is affected for sure. For lower frequency of clocks, more time. For higher frequency of clocks, less time, that we can see from this equation. But since we have both the readings taken from the same clocks, and assuming that during integration and deintegration time we have this one fixed clock, whatever be that value, even 8% lower or 8% higher, doesn't matter. We have the same frequency for integration and deintegration time. So the time will be affected, but still the overall value, that is Vx value, will be unaffected, because what is it? T2 by T1. So T2 by T1, the scale will be still same, because it is from the same clock. Same clock, although slower. So T1, T2 dash value will change, but the scale is still unaffected. So Vx is unchanged. So this is the answer. Okay. Now see the second question. Okay. I hope in the previous question you don't have any doubt, because that was the foundation problem, the very first problem. So with this knowledge, now try the next question. I'll give you some time to just read the problem, and if you can, some of you can unmute, or some of you can want to discuss, you can always discuss. Just read the first problem, sorry, second problem, and then
सर
try.
लास्ट वाला क्वेश्चन फिर एक बार रिपीट कर दीजिए सर.
ओके, कौन सा वाला बोलिए, कहाँ पे?
थर्ड वाला सर.
हाँ देखिए, आपको यहाँ पे क्या बोला है, व्हाट इज इट गिवन, दैट द क्लॉक इज नाउ स्लो. बट वो स्लो जो क्लॉक है, उससे ही आप इंटीग्रेशन टाइम में भी टाइम मेजर करेंगे इन फॉर्म ऑफ साइकिल्स, और डी इंटीग्रेशन टाइम में भी आप टाइम मेजर करेंगे इन फॉर्म ऑफ साइकिल्स, क्लॉक साइकिल्स आई एम टेलिंग. सो जितना भी आपका क्लॉक्स आएगा उस स्लो टाइम के वजह से वो थोड़ा ज्यादा आएगा, और इन द नेक्स्ट डी इंटीग्रेशन टाइम ऑल्सो इट विल बी मोर, बट इन द सेम प्रोपोर्शन. वाई? बिकॉज ऑफ दिस इक्वेशन. तो आपका एफ जितना गुना, how much times your f is affected, that much times your time will also be affected, the clock time I am telling. So accordingly T1 by T2 will not change, but T1 T2 will change. That is the whole point. So Vx value is still same. That is what I am telling. The clock, due to the change in frequency of the clock and change in duration of one clock period or one clock time, your time of measurement will be affected, but still the time scales, since you have two times with the same clock, although it is slower or faster, your scale will be still same. That is the ratio of T1 and T2 will still be same, and ratio of T1 and T2 will give you Vx multiplied by obviously Va from this equation. So that is why its value is still not changed. But can you tell me one
Yes,
thing?
sir.
That this one, this peak will change. Why? Because T1 and T2 are now changed. And if you want to maintain the same peak, then you have to integrate for more time, because your clock is now slower. Got it, na? To get this value, you have to now integrate for more time, because your clock is now slower. Your T is now more, taking
Yes.
more time. Due to the slow clock, your time taken is more to reach the same value. Or if you don't give the same time, then your peak will be low. So accordingly, you can just understand how you can frame, because all those data needs to be provided to you. Then only you can answer the separate parts. But clock is now slower. You will take more time to get the same value. That is understandable. That the scale is still unchanged. That is the main point. So reading will be same. So try the
Yes, sir.
next
Got it.
problem. Try the next problem. So now they have already specified that is a single slope ADC, and the peak value is given to you. Just the peak value we were discussing, just the peak value of measurable voltage it is given. The counter, whatever is the counter, has 10 bits. So from this information, now you have to determine the resolution. and the maximum input value of the voltage that can be obviously converted into a measurable form, and the maximum time required for a conversion, and the ramp rate. 4 options, 4 parts are given, asked in this problem. So A, B, C and D. So kindly solve, okay? Otherwise you will not get it. First part I think you can try, then the following parts. Yes, just try, okay? Yes, someone has written, yes, the maximum value of the input voltage is obviously that is measurable is nothing but the peak value of the ramp. So that is nothing but 5 volts. So this part you should have all answered, right? So next part you try the resolution. Resolution you try. Yes, this is easy. I think you must have gone through ADC and all those things. So what is the meaning of 10 bits or n bits? So how many combinations? Possible to represent, that is how many discrete representations you can form from 10 bits. One bit can take only two values, 0 and 1. Second bit can also have two values. So what are the total number of possible combinations? 2 to the power n combinations, and every combination you can map with a certain value. So how many combinations possible? 2 to the power n. Now maximum value is 5 volts. This is maximum. Divided by 2 to the power n combination. That is, if you have so many combinations, then one combination can lead to one small value, that is the smallest measurable value or the least count. That is what is the resolution. So what is that? 5 by 2 to the power 10. You give me the answer in millivolts. I think it is 4.88 millivolts. Yes. So now you try the next part. Part C. Maximum time required for conversion of the value of the voltage to be measured into the measurable form. What is the maximum time taken for the conversion of the measurement, right? So give me the time. So next two parts. Anyone? Yes. So it is the maximum time that it can take to measure obviously the maximum possible measurable value. What is it? Nothing but 5 volts. So to measure 5 volts, what is the time it takes? That is what it is indirectly asking. To measure 5 volts, which is the maximum possible measurable voltage, that is taking the maximum possible time for conversion. So one clock, you know that it gives in 20 kilohertz, and you know the resolution also. So try to find with that value what is the maximum possible time. So one, I can tell one combination, it takes 1 clock period. So 5 volts is the maximum measurable voltage, which is the 2 to the power 10th combination. So it is taking 2 to the power n clocks. And what is the time of 2 to the power n clocks? Because 2 to the power 10 clocks will be taken to measure 5 volts, which is the maximum possible measurable voltage. And for measuring that, how much time is needed? It is the time of 2 to the power 10 clocks. And what is how to find that 2 to the power 10 clock time? It is multiplied by 1 clock time. 1 clock time multiplied by 2 to the power 10. So what is 1 clock time? It is nothing but 2 to the power n into 2 to the power 10, I think, divided 1 by clock frequency, which is 20 kilohertz. So tell me this time. Give me this time value in milliseconds. So again, I need to multiply with 10 to the power 3 to derive the answer in milliseconds. So 10 to the power 3 and 3 cancelled. Then I need how much? 2 to the power 10 by 20 milliseconds, whatever it is coming. (51.2 milliseconds). Yes, correct. So that is the maximum duration it will take to measure the complete maximum peak voltage measurable. That is nothing but the time. They are wanting peak value to time conversion. Time conversion how we'll get from the bits. So that thing you should know. And what is the final? Ramp rate. So ramp rate is what? Maximum voltage by maximum time. Maximum measurable voltage divided by maximum time taken for measurement. Like this you can also write. So what is it? How can I write it? It's 5 volt divided by volt per second. Please note, it is asking volt per second, not millisecond. So 51.2 into 10 to the power minus 3 is volt per second. So how much it is? It is coming as 5000 divided 51.2. It is 97.65 volt per second. Okay, that is the answer. Then let's go to the next problem. I think no one is having doubt, or if you have some doubt in any stages of the problem, kindly ask.
सी वाला रिपीट कीजिए सर थोड़ा सा.
हाँ, सी वाला में क्या है? Estimate the maximum time required for conversion. That is, it is asking the maximum time taken by the measuring instrument to measure the maximum possible measurable value. Maximum possible measurable value is how much? 5 volts. तो इसको measure करने के लिए how much time is required? So to measure 5 volts, how much time is required? That is it is asking. So you know that to measure one combination, it takes one clock. So one combination comes from one resolution cycle, one resolution measurable voltage, I can say. So what is the one resolution measurable voltage? It is nothing but yes. Can you tell what is the one clock time? It is nothing but 1 by clock frequency. This is one clock time, right? 1 by frequency is nothing but 1 by clock time. So for one smallest
Yes, sir.
voltage measurement, it takes this much time. That is 1 by 20 kilohertz. So now to measure 2 to the power 10 such combinations, which is the final combination of the 5 fold. Because how much combinations it will spend or how much clock cycles it will take to measure 5 volts, 2 to the power 10. तो 2 to the power 10 क्लॉक साइकिल्स का टाइम क्या है, यही आपको पूछा गया है. 5 volt is the maximum possible measurable voltage. It will take the maximum possible clock cycle. So what is the clock cycle? 2 to the power 10 from the bits. How much time will it take? 2 to the power 10 multiplied by 1 clock time. 1 clock time बोला तो 1 by 20 kilohertz. वही लिखा है यहाँ पे.
Yes,
this
sir.
one. ठीक है?
Okay, sir. Got it, sir.
Okay, now you go to the next problem. I think the next problem is visible on your screen, right?
Yes, sir.
Yes, so kindly try it. Yes. So now we have a successive approximation type register, a 20-bit ADC driven by a 4 kilohertz clock. So now you have asked how long does it take for the ADC to convert the input volt? That is how long it takes for the measurement. That is, it is asking. In milliseconds you have to give. Please note. These are the important things you have to know. Otherwise, problems are simple if you understand the concept, right? So please take care of the units, kilohertz, milliseconds. These are important. And then the bit information, right? To know about the resolution. Just like we discussed in the previous problem. If you know the one combination value, then how to calculate for the complete measurement value. That is, you have to take the combination multiplied by one clock time, and then you get the total time. Because time in discrete digital measurements is only because of clocks. So if you know one clock time and you know total counts, then you can get the total clock time, which is nothing but the time taken for the measurement. Hope you understand what I am telling. So with this concept, you go ahead and try to determine this problem, well, the time taken for the measurement, obviously in milliseconds, right? So try this problem. So can anyone tell me for a n bit successive approximation register, how many clock cycles it takes? Because we just saw that in the digital ramp type n bit voltmeter measurement, how much we needed? Yes? How much we needed for this? We needed 2 to the power n clock cycles, right? But for SAR, how much clock cycles we need? Same, n bit. Both are n bit. Yes? We need log of 2 into number of combinations, which is nothing but log of 2 to the power n. Same for n bit 2 to the power n combinations are possible, both for these two. But the number of clocks in this required is log of 2, then 2 to the power n, which is nothing but n. So n clocks only needed, which implies it is faster, right? Much faster than digital ramp type voltmeter version. So please note it. So now with this information, can you tell me how many clocks, or how many final answer you can tell me that if it is a 20-bit ADC, then how many clocks it need? ADC based SAR I can write. For a 20-bit ADC based SAR, how many clock it needs? It is 20 clocks only. So for 20 clocks total, then how long you take to measure? One clock you take 4 kilohertz. Then for 20 clock you take, sorry, 1 by 4 kilohertz. This is a time. So then you take 20 by 4 into 10 to the power 3 in time, which is nothing but 5 milliseconds. Any doubt? Yes, correct answer. Okay. Whoever has written 5 milliseconds has understood the problem. So his answer is correct. So like this, you have to first determine that what is the particular application, and accordingly you have to determine the number of cycles, clock cycles, and then from clock cycles determining the time is very easy. If you get the clock cycles, know the frequency f, then time t is nothing but c by f. C into 1 by f. 1 by f is the time. C into time is the number of clocks, is the total time, right? Total time. So total time is nothing but c by f. Any doubt? You can just let me know. So SAR is faster. That is the whole point, right, of this problem. Now you can tell me the next question. See the next question, okay? So how many comparators are needed for 16-bit flash type ADC? So it is a 16-bit flash type ADC, and they are asking you the number of comparators. Yes. So number of comparators is 2 to the power n minus 1. Is nothing but 2 to the power 16 minus 1, and it will give you 65535. a simple problem because it just asks you to find the number of comparators. And number of comparators is nothing but 2 to the power n minus 1. That is the answer. Okay. Now with all this information, what you can conclude about the speed of these three different types of measuring instrument: successive approximation type, digital ramp type, and flash ADC type. How can you compare their speeds? Which one is the fastest, and followed by which one, and then which is the least or which is the slowest in measurement? Yes, which option is correct? Yes, you think we have already discussed, right? One thing you know that third is faster, right? Then what? Digital ramp type, right? But the flash one is the fastest. It only requires one clock pulse. So flash requires only one clock pulse. SAR requires, for a n bit, I can tell, requires n clocks, and n bit digital ramp type requires 2 to the power n clocks. So this one is the slowest. This one is the medium speed, and this one is the fastest, the flash type. So flash type is the fastest, followed by the successive approximation type, and then followed by the digital ramp type. So this one is the possible correct option. So which one is the fastest? Flash, then successive approximation type, then digital ramp type. So option B is the correct option. Okay, I hope you understood the reason, right? Option B is the correct one. So now you just see the next question. Okay, with all these information, I hope we have gone through the basics, and now let us delve more into the numerical part. So try this problem. Okay, a 8-bit DAC has a resolution of 0.25 volt. So resolution is already given. How much is the smallest voltage it can measure, and the DAC is of 8-bit. And so now you have to answer what is if. That is, what is a DAC? DAC is digital it gets, and some particular, it corresponds to some voltage level. Just like we saw that the 2 to the power 10th combination, which was 1 1 1 1 1 and then 1, 10 ones, it corresponded to 5 volts. So a 10 bit, if I give you DAC, then the highest possible level, which is 5 volts, if we can measure, then that corresponds to the 2 to the power 10th combination, which is nothing but 1 1 1 1 1. So that corresponds to the highest level. Similarly, in a 8-bit DAC also, every combination, there are 2 to the power 8 combinations. So every combination corresponds to a certain voltage level, because you are already dividing the peak value, peak measurable voltage, by the number of combinations, which is 2 to the power 8. So every combination will correspond to a particular voltage level, incremented from the lowest level by the resolution value. Okay? So every combination out of the 2 to the power 8 different possible combination corresponds to a certain voltage level. This you remember, and hope that will help you to solve the first part. So if the combination is this, then what will be the output is asked. In voltage, obviously, what will the output of the DAC? Yes, so try this problem. Yes, correct. whoever has told 5 volt, he is correct. So how to determine? Resolution is given 8-bit. Then you just convert to what? You just convert to the. Can you tell me how to do this problem? So we want what is how much combination, what is the level of the combination? The 0th level or the first, then second, how much is the level of the combination? So every level of the combination incremented, it gets incremented by one resolution of the voltage. No, why you are converting to decimal, that they need to understand. If we do mechanically, then everything is one line problem. But why you are converting to the decimal form? You need to understand. Why this decimal binary representation we need to convert to the decimal form is because in every form of representing the combination of the digital form, we are incrementing that by one resolution step. So if I give you this decimal form, which is a 8-bit decimal number, then is it the first combination? First combination is 0, 0, 0, 0, 0, 0, 0, 0. I hope it is 8-bit. Then next combination is this one. Then next combination is 1, 0. So this is the 0th combination. Then this is the first combination. Then this I call the second combination. So as you see, it is same as the decimal number. So the binary form, if I convert to the decimal form, I am getting the order of the combination. So it is the second order. It is the first order. It is the 0th order. So now, what is the order of this combination? Can you determine 0, 0, 0, 1, 0, 1, 0, 0? So simple. It is the LSB, lowest significant bit. So 2 to the power 0, then 2 to the power 1. Similarly, you do up to 2 to the power 7. So to all those are with zeros. So I neglect. And this is the what position? 1, 2, 3. So 2 square is having a 1, and then 1, 0, 1, 2, 3, 4. 2 to the power 4 is also having 1. So you add them up and you get 4 plus 16. It is 20. So this particular combination is what? Is possessing a voltage value of 20 times your resolution value. Because every combination, it incremented by 0 to 1, it incremented by plus resolution, 1 resolution. Then 1 to 2 incremented by 1 resolution. Then in 20, it incremented by 20 times the resolution value. And that is what is the voltage, corresponding voltage. So what is it? 20 times resolution. 20, how it came? Equivalent decimal form. So what is the resolution? 0.25. So 20 times 0.25 is nothing but 5 volts. Any doubt? Any doubt?
No, sir.
Okay. Then try the second problem. Just the reverse. If you want it to be 10 volt, now what should be the binary number? If you understood this part, I hope you should understand this part also. So what you get? Analog value or analog voltage is nothing but what? Combination order times the resolution. That is the first combination or the second possible combination of the 8-bit DAC, just like that. So what combination order corresponds to the 10 volt? Just to find that 10 volt we need, and for that what combination order we want to get? Resolution is resolution is 0.25, it is given already. So what is the combination order? Yes, It is 40, right? So what decimal value corresponds to 40? Yes, 40 to binary. How to do that? Any idea? How to convert 40 to binary? Simple, right? You just keep on dividing by 2. It is 0. Again you divide by 2. It is 0. Again you divide by 2. Yes, it is 0. Again you divide by 2. It is 1. Again you divide by 2. Right? So how many you are getting? 1, 0. From here to here you write 1, 0, 1, 0, 0, 0. But how many bits are there? 1, 2, 3, 4, 5, 6. But 6 bits are not here. It is a 8-bit device. So you add 2 more zeros. Nothing will happen. So this is the DAC input. So if DAC receives this input in analog, it will correspond to 10 volts with this resolution, 0.25 volts. Any doubt?
No, sir.
Okay, I hope you know how to convert decimal to binary. Only that is needed. So now you see this one, this problem. Yes, yes, please answer. Someone is writing in the comments. You want to discuss something, you can just unmute and just discuss. Someone is having some doubt, I think. So let me go back. Yes. Yes. So what is the doubt? If you have any doubt, you can just let me know. Okay. Okay. So just see the next problem. So the resolution is already given to be 0.1 volt, right? And then it is also given that the measurable range is 0 to 10. Then how many bits it should have is the question. So resolution given, peak voltage given, then bits asked. Now resolution given is the actual indication of the bits. It corresponds to the bits. So from that you can actually easily determine the number of bits. Because why? Because if it is a n bit ADC, then it has 2 to the power n combinations. And every combination will correspond to a voltage level. But the total highest combination will correspond to 10. So one combination corresponds to 10 by 2 to the power n volts, which is nothing but smallest possible voltage, which is nothing but resolution of the device, which is given to be 0.1 volt. So you equate 10 to the power 10 by 2 to the power n to 0.1. Tell me how is n coming? Yes, please tell. Yes, what should be n? Yes. How you determine? You just need to take an integer value. It's always integer. So now if I just try to check that what is it, so 2 to the power n is coming to be around 100. So if I do 2 to the power 6, I am not getting 100, right? Let us do 2 to the power 6, it is 64. 2 to the power 7, if I do, we are getting 128. So it is a number between 6 and 7, which is not possible because n cannot be fractional. So we need to always take the highest one. So n is 7. Take the highest integer. Because we need to satisfy this condition, right? So n is taken as 7. So 7 is the answer. Hope it is clear, right? So solve these two problems. Here are the two problems. Just see. Please try these two problems, okay? Okay. So can you please explain by unmuting how to solve? Someone just gave the answer. So let me check. But how you solved? Yes, someone wants to discuss their ideas. Yes, I think you are not audible. Yes. Any answers? One answer I got. Some other answers? But the answers I got, I think it is not correct. So the next problem they are asking the quantization error, okay? And the first problem they are asking the number of bits, minimum number of bits that the ADC should have. Anyone wants to try? I'll give you 1 more minute. Just try, okay? Yes, anyone has done the first problem? If someone has done or they want to discuss, they can just unmute. So quantization error is already given, right? Quantization error, can someone tell me what is quantization error? Is the error between the voltage levels which you cannot measure. You have to surpass that for the least count. That is same as the least count of a measuring instrument. You cannot measure between the least count. Similarly, during the quantization error, that means when you are quantizing the voltage levels into some discrete and assigning some discrete, I think, combinations, then you surpass some voltage values, because voltage is a continuous value. It is not a discrete value, but you quantize both in time and in your voltage. So during the quantization, you are surpassing that least measurable voltage. Within that, you cannot measure. So that is the least possible measurable voltage, or your limitation, that is corresponds to the least count or resolution of the measuring instrument, right? So that is given as 0.25. So now what they are asking is the number of bits. So number of bits is nothing but peak value by number of combinations. So please note this value, note this word, right? Yes, that is what I am coming to. Sorry, this will be resolution, right? If you divide the peak value with the smallest measurable value, then you get the number of combinations, right? Not number of bits. None of you are telling me. It is not the number of bits that it will give you. Dividing the peak value with the smallest measurable value will give you the number of combinations. Yes. So now how to determine the resolution? Peak value is given to be 10 volts. Resolution is what? For 0.5 of the half least significant bit measurement, that is half of a bit measurement, it has it corresponds to half. So what it is giving? 0.5 LSB corresponds to 0.25 volt, but we need at least one bit. During 1 bit increment, how much is the error? So it is nothing but a way of saying, and you multiply it by 2, because for half bit, if you are getting that much voltage level quantization error, so what is the actual, because we increment by bit in every combination. I showed you, 0, 0, 0, 0, 0, 1, 0, 1, 0. So 1 bit it is incrementing every combination. So in every combination, every corresponds to 1 bit. So 1 bit corresponds to how much quantization error shift. So that is nothing but the half into half times it is given. So you need to find the full quantization error. So it is nothing but 0.25 into 2. I hope it is clear. Now it is 0.25 into 2 will give you the number of combinations. Is nothing but 10 by 0.5. So it is giving you 20 possible combinations. So how much is the bit? 2 to the power n corresponds to 20. But I need n as an integer. So what is n min? Minimum possible n. 2 to the power, how much should I give? N value? Try. Yes. 2 to the power 4?
5, sir. 5.
Yes. 5. Because 2 to the power 4 is also less than 20. So 5. Yes, correct. Correct answer. So 5 is the answer. So this is the correct answer. I hope you got it. Got how to actually do the problem. Then using similar analogy, a reverse form of the problem you can do. Just try. The second part I can tell. Yes. Please try the second part. Using same analogy, right? Concept is remaining same. Only the forms are changing and they can ask you anything. So you need to be fluent with the concept. So try. I will give you 1 minute. Because these kind of problems are very small, right? If you understand the concept, it is one line only. Should not take more time. So what is the quantization error? Minimum quantization error. It should be one line, right? Right? Now you should do it fast. Slowly you should increase the speed. So what is the quantization error? Just follow up. It is nothing but peak value by 2 to the power n combination. Number of combination. And where from we get the number of combination? From the number of bits, which is given to be 8. So peak value is 5 divided by 2 to the power 8 is the minimum quantization error. So now tell me quickly, what is the minimum quantization error you are getting in volts? Yes. Yes, but one point you forgot. We have to do a -1. Because the number of combinations, agreed that number of combination is 2 to the power n, but the quantization is happening after 0. So I hope you are getting what I'm telling. Means that from 0 it started, and for example it has 10 such combinations. So the quantization is happening from here to here. Just like the problem that between 10 trees, how much space you have? You have 9 space. So quantization is coming in between. So it is better you do a -1. So 2 to the power n combinations possible, but how many steps are possible? So it is actually not number of combination, but steps. Number of combination correct. In all the previous problems where the number of combinations was necessary, it was correct. But when we need the number of steps in this problem to deal with the quantization error. So number of steps, if they ask, it is 2 to the power n -1. So number of steps. Just like the problem I discussed, that between number of trees, 10 number of trees, you have 9 spaces. So 9 steps that it has to increment. So it will not cause a very significant shift, but still going with the accuracy, we have to determine the minimum quantization error, and it happens every step of conversion. So 5 by 2 to the power 8 -1. What it is coming? So it is number of steps, not combination, right? 2 to the power 8 -1. Yes. So what it is coming? 5 by 2 to the power 8
0.019.
Yes. So in millivolts, it is 19.61 millivolts. Correct? So now see this one. I hope the problem is visible on your screen. Yes. Please solve this problem. So it is asking the time in microsecond for the ADC to convert the voltage into measurable form, into the digital form, because it is a ADC, right? So analog voltage, it converts into the digital form. So how much time it takes? And it is a digital ramp type. sorry. So it is a digital ramp type, 10-bit ADC, not successive approximation type, and it is driven by a 100 kilohertz clock. So time for conversion is being reduced. Yes. Anyone solving? It is a one-line problem, right? So total time taken is number of steps multiplied by 1 clock time, just as we discussed before. And how many steps are needed? 2 to the power n minus 1. Because to measure the total voltage, you have to have some combinations. For the 10-bit, you have 2 to the power 10 combination and 2 to the power 10 minus 1 steps. So that those steps should be incremented every clock time to give the time. Total time is 1 by 100 into 10 to the power 3. This is the time. So for 1 clock, and total number of clock increments is 2 to the power n minus 1. Because from 0 to 1 you need 1 clock. Similarly, from 1 to 2 you need 1 more clock. So between 2 to the power n trees, there are 2 to the power n minus 1 steps and 2 to the power n minus 1 clocks. So every clock time. This will not cause a very significant deviation in your estimation. So don't get confused. Even if you take 2 to the power n, it will not give you a significant deviation. Because somewhere we take positive edge as a measurement and then falling edge of the clock as another measurement. It will not cause a very huge deviation. So even if you do 2 to the power n, it will not be a significant error. Hope you understand what I'm telling. So it depends, okay? So now you calculate 2 to the power 10 minus 1 multiplied by 1 by 100 into 10 to the power 3. This much is the time, but they want in microseconds. So you multiply 10 to the power 6 and then divide by 10 to the power 6, and this is in seconds. So you give me this value, and this will 10 to the power 5 in microseconds. So I have 1, and then we have 2 to the power 11 minus 10 microseconds. So you do this. Sorry, 2 to the power 10. This will be this only. So this is not correct. So 2 to the power 10 minus 1 into 10. This is not 2 to the power 11 minus what I wrote. That was incorrect. So 2 to the power 10 multiplied by 10 minus 10, 10 to 30 microseconds. Yes, that is the total time. Yes, that was incorrect, not 2 to the power 11. Correct. Yes, answer is correct. Whoever gave the answer is correct. Okay, any doubt in this problem? So answer will be in microseconds. That's why we multiplied and divided by 10 to the power minus 10 to the power 6 and then 10 to the power minus 6. Okay. Any doubt? Okay, so we go to the next problem. Try this. So again, they are asking you the time. But note, it is in now a successive approximation type ADC, not the previous one where it was a digital ramp type. So time is number of combinations or number of steps multiplied by 1 clock time. I told you for SAR it is n. N clocks required for the measurement, for the n bit, for n bit SAR. There is a maximum possible time it will take, and 1 by 100k. So equal to 10 into 1 by 100 into 10 to the power 3. That is the time. But we want in microseconds, to multiply and divide by this. And this goes to microsecond. And what is it coming? Yes, someone gave answer. So calculate this part, others. 10 to the power 7 by 10 to the power 5. So 100 microseconds. Correct? So 100 microseconds is the answer. Any doubt? Same concept we are following, but only be careful of the type of ADC. The type of ADC decides the number of clocks required for it, for the measurement. So please be careful, okay? Okay. So I think this question needs another line. Just let me check. Some line regarding the yes. So I will specify the complete line. A linear ramp type ADC is required to convert 0 to 5 volt input, obviously to digital form, within 10 milliseconds. at max. Then with this given question information, you are needed to calculate these three subparts. So can you see the problem on my screen?
Yes, sir.
Okay, so please solve this problem. So it is a linear ramp type ADC, right? And it is required to convert 0 to 5 volt, which is the range input, analog input, to the digital equivalent form within 10 milliseconds at the maximum. So it is giving you the maximum possible time, which we are deriving for so long. Time is given now. Maximum possible voltage is given to be measured, and it is linear ramp type. So three things you have to calculate now: minimum required peak value of the ramp, minimum required slope rate, and speed. Three things you need to calculate. So minimum required peak value is nothing but 5 volts only, right? And minimum required slope rate. So slope rate is nothing but, can you tell? Slope rate or ramp rate? Yes. And speed also you tell me. Speed in frequency, that means. So it is asking minimum required slope rate, right? So this is nothing but resolution divided by total time. So what is the resolution? To write it in a better manner, yes, can you tell me the what I can write? This is nothing but 5 by 10 also you can write. It's 0.5, right? 0.5 milliseconds. Or resolution by one small clock cycle time. Both you can write. So either way is correct. Total time period, and then from that one clock time period you determine, and you determine, because it is a straight line. So one small clock and one resolution for total peak value and total time. Both will be same, right? Because we need the slope, which is known as ramp rate of measurement of that integrator. We need the slope. So minimum required slope is also this one. From the minimum required voltage it came. And what is the minimum required speed? Can you tell me? So can you tell me how many bits from the time? Can you tell me how many bits? So time is what? Number of combinations multiplied by 1 clock frequency, 1 clock time. And we already know. And this is the minimum speed of the clock being asked. So we need the number of bits, right? I guess this one is given, right? Yes, so what we need is this thing. One inverse of that thing we need. So if I write it as 1 by speed or 1 by frequency, because that corresponds to the frequency. So I can write speed is number of combination, or you can write counter value divided by time, total time. Agreed? And also one more thing, you know, that number of combination is nothing but maximum value. How can I write? By how can I get the number of combination? From the bits, right? Yes. Maximum value by resolution. So how to get the resolution? Do we know the resolution? We neither know the resolution nor the number of bits, right? I think number of bits should be specified in this problem. Any of either of the one information, either the number of bits to know the number of combination or the resolution should be specified. So you can assume a 10 bit, okay? 10 bit you can assume, and then you can determine the speed. So speed is nothing but 2 to the power 10 divided by total time, which is 10 milliseconds. So what is the speed coming or frequency? 2 to the power 10 divided by 10. However, milli will become kilo. So 102.4 kilohertz is the speed or frequency of counter. There is the clock, frequency of the clock. And it also sets the speed for the counter, right? So it is nothing but the same. So now coming to the next problem, that if you have a perfect linear ramp type digital voltmeter and suddenly ramp rate becomes slower, which we were discussing. The ramp rate is now slow. That is the integration rate. Now everything else is unchanged. Now will your value of the voltmeter, that is your voltmeter reading, will it change or not? We know that CV times T1 equal to same multiplication constant into Vref times T2. This is the de-integration time, and this time is this T2, and this T1 is the integration time. And C is the constant which sets the speed of the integration. So now it is telling that if the ramp rate is slower, so this is slow, then will it cause any change? That is what it is asking. So I can write unknown voltage, which is Vx, is what? Counter value by frequency into ramp rate. because what? Vx is Vref into T2 by T1. And this is the ramp rate. And T2 is what? Nothing but counter value by frequency. Because time is what? Counter value by frequency. So that is what it is written here. So nowhere in this expression you are getting that your, or you tell me what will be the answer. Rather than directly telling what should be the answer. You know this expression, right? Of the ramp type digital voltmeter. So now what can you comment? Yes. So the ramp rate becomes slower. So not the time that, or a time parameter or a amplitude parameter, only one of that became changed for which the ramp rate was affected. Now if the ramp rate is affected, that is it is lower, that is it is slower, you can tell, then the unknown voltage value will be directly affected. But if the rate changes, then not the integration, but the ramp rate they are telling. So then the value will be what? Lower, higher, or what? Yes, someone is telling A, that is more than the correct value. Okay. So slower means more time or less time? Yes. So what will happen? The counter value will increase and it will lead to more, that is, if you are slowing down the ramp rate, it will affect the counter. Counter value will increase for the same voltage measurement I am talking about. To measure the same voltage, it will take more time. So, but if you provide, that is the slower ramp rate, then it will show the more value of the unknown voltage because of the increased counter value. Is this clear? If anyone has
Yes,
doubt,
sir.
kindly let me know. So now try this. No, it is not C. So here in the previous problem, you don't have two voltages, right? It was a single ramp type digital voltmeter, right? So can anybody explain what happened? Just coming to the previous problem, if you would have needed to measure the same voltage value, then for a slow ramp signal, you would have needed more time, right? Agreed or no? Just like this. So, but now your ramp rate increased. So you are getting more value. Which one are you telling? See the next problem. This one. Okay. There is a perfect linear ramp type digital voltmeter. Suddenly clock becomes slower. Okay. So say that is what I am telling. For a single type, not dual slope type, if clock is now slow, what will happen? So you guys are confusing with the dual slope type. Just recall the lecture. We are not doing two measurements with a reference value. I hope you are getting what I am telling. You are confused with the two. But we are doing a single measurement where now the clock is slow. If the clock is slow, what will happen? Just check here. This bold formula.
B, sir.
Yes, B. So now clock is slow, right? So every counting is done for a longer time. So it will not be able to reach the actual value. Every counting takes longer time. So if every counting takes longer time, then what? For the same time, you are able to measure lower value. You need to interpret what they are telling. So option B is the correct option. So similarly, now you come to a dual slope type voltmeter. That is what you are confusing with. Now if the clock becomes slower, then it is not an question because you are measuring two times, as I told you, T2 and T1. Then if you are measuring two times, everything is measured slower. And once you compare, then you cancel the effect of, even if they are changed, still Vx is unaffected. Why? Because T2 dash by T1 dash is constant. Hope you understand. So it is same as the correct value. Option C is the correct answer. Yes. So with this, we come to the end of the discussion and hope you have understood the concepts, and if you still have some doubt, we can discuss in the group. So we have one group, hope you know, but still I want to share the group link with all of you again. And you can also join this group because otherwise your attendance is very poor in this. So I request you to join this group so that you can be updated. If you have some doubt, you can just post. and you can be updated of the sessions, right? I request all of you to join this WhatsApp group. I have already shared in the chat box. And sessions are held every Saturday, 7 p.m. to 9 p.m. And the additional session, the 13th session, the final session which I was talking about, is also going to be held in the same day, Saturday, 7 to 9 p.m. So we have 4 more sessions left, and I request you to join the sessions, because that will be helpful for you for solving lot of problems and concepts that we are discussing every session. So I hope all of you should join the group. And with this, if you have no doubt, I want to end the lecture, right? Okay. So thank you very much.
Okay, sir. Thank you, sir. Thank you, sir.